Hello and welcome everyone. On behalf of our JCAP team and Caltech, it's my pleasure to welcome you to our virtual 2020 Solar Fuels meeting and to the third webinar. Today's webinar will focus on future directions for solar fuels field. You can find more information about the meeting, including posters and keynote presentation on our website, so I encourage you to check it out when you have a chance. I put the link into the chat here in Zoom. As a kind reminder, please use Q&A feature in Zoom to submit your questions. So we're gonna have a live discussion is gonna run until 10:15 today, 10:15 a.m. Pacific daytime. And then we'll have additional 15 minutes to answer more questions online. So we'll try to answer as many questions as we can. So without too much delay, I would like to introduce today's moderator, Dr. John Gregoire. So John is the key investigator in the JCAP program. He's also photocatalysis thrust coordinator and the principal investigator for the high throughput experimentation laboratory at Caltech. John's research interests center on accelerated materials discovery by incorporation of automation, theory, and artificial intelligence in experiments. Also joining us today is Owen Rimolu. She is a PhD candidate at UC Berkeley, and she's a member of Alexis Bell and Adam Weber's research groups, and also a vital member of our JCAP team. She studies the electrochemical reduction of carbon dioxide in membrane electrode assemblies and works closely with scientists and engineers on the design, operation, and characterization of solar fuels generators. Joining us today is Shane Ardo. Shane is an associate professor of chemistry at UC Irvine. Shane's research group is focusing on understanding and controlling reaction mechanisms at interfaces with the goal of maximizing energy conversion efficiency for realistic applications, including solar fuels devices, photovoltaics, solar seawater desalination, and redox flow batteries and fuel cells. And finally, we have Jason Cooper here with us today. Jason is a research scientist at LBNL and a key member of JCAP research team. Jason's primary focus is on understanding the electronic structure of new materials. He's using spectroscopic and computational methods to better understand the carrier physics with a goal to improve processes such as carrier recombination, transport, and energetics favorable to solar water splitting and also CO2 reduction reactions. So thank you, everyone. And with these brief introductions, I'm turning this meeting to John. Thank you.
Thank you very much. And I want to thank the organizers for setting this up and giving us the opportunity to have a conversation this morning. So in the first two webinars, we covered, in this series, we covered water splitting and CO2 reduction in a level of detail and touched upon some other topics like societal implications and the level of integration we foresee in devices and the need for a new kind of research workforce. And we're going to touch upon some of these topics today in a different vein and introduce some new ones as we look at the emerging evolution of the scientific landscape of what we broadly refer to as artificial photosynthesis. So before jumping into the artificial version, we're going to look at the left-hand side of this slide and natural photosynthesis, which is really a marvel of evolution and has inspired scientists, scientific endeavors for a very long time. And why it's really intriguing and really a marvel is the number of different functionalities that it incorporates into a network of biological phenomena. So it captures carbon dioxide and water from the environment and converts those to plant fuel and performs fuel separation and storage and critically does its own self-repair. And so in artificial photosynthesis, we've been successful at kind of emulating some important features of this, but not all of them. And instead of kind of ubiquitously powering plants around the world, we have working prototypes in dozens of different laboratories with different strategies and levels of kind of getting onto a technology readiness scale, but not really there establishing this technology in industry yet. And there's a lot of reason to be optimistic about the near future, especially given the rapid progress that's made in the last 10 years with efficiency records being set fairly routinely now as we advance our scientific understanding and translate that into devices. And some particularly exciting work on converting CO2 to useful fuels. And so as far as kind of comparing where we are with artificial photosynthesis compared to natural photosynthesis, we've pretty successfully done an analog of the photogeneration of electrons and using those to perform oxygen evolution from water, which creates the protons, frees the protons and electrons that are used for fuel synthesis. And on the fuel synthesis side of the device, it looks a lot different than what the plant does. And it probably should, because we're trying to make fuels to power all of our technologies and life's activities, as opposed to the plant that's powering the growth of itself. And so in kind of light of some similarities and some differences and maybe some aspects of artificial photosynthesis that we have yet to emulate but could, we're going to look at kind of a broader landscape and recognize that we're always building on a scientific foundation of semiconductor photoelectrochemistry and electrochemical CO2 and N2 reduction and other areas of science. And in the last century, the kind of trunk of growing out of these fields is the concept of sunlight to fuel. And we did hydrogen fuel and carbon containing fuels in the last webinars. And that's why, this is really the core focus of the field. But we've recently been seeing a lot of branching out, and we think that's going to continue involving CO2 capture from air, integration with biocatalysis, creating more than fuels, commodity chemicals with similar processes, and the use of intermittent electricity from renewable sources. And so as we go through this webinar today, we're going to envision the future of solar fuels technology by recognizing recent evolution of the field, discussing emerging opportunities and how science can realize them, and imagining the broader scope of sustainability technologies that will co-advance with solar fuel science. So with that, I'll ask the panelists to jump back on here. And while they're doing that, I'll get started with the first question, looking at recent history and what changes have occurred in the solar fuel research field that are really changing the course of the field. And I'll start with an opening remark from my own opinion and then turn it over to the panelists. I think something I've been really excited about that's really taken form in the last 10 years is generally what I'll refer to as kind of embracing systems science. And the hallmark of fundamental catalysis work is in well-defined conditions. And as theory has developed improved methods and used explicit solvent models, and as operando experiments have really grown in sophistication in the last several years, we're learning that the dynamic environments of operational catalysts in devices is really opens a broad avenue of new directions of scientific research. And this is complementary to the well-defined conditions, but really it's when I think 10 years ago, if you said a system, people think engineering, and now we're saying actually system science is maybe where the most challenging aspects of fundamental science exist. And so to answer the same question, I'll ask Oyen to provide an additional response.
Yeah, thanks, John. For instance, biomolecular or bioelectrochemical systems called BES and microbial electrochemical systems, MES, and enzymatic systems have been of increasing interest in the past decade or so for a number of reasons. With certain microbes or cultures, there's the possibility and flexibility of us tuning the product stream selectivity. And there have also been some increases in efficiency in these types of systems in the past couple of years. With these systems, you can also operate under mild or ambient conditions, and we can also use less hazardous chemical substances. So in all, these BES and MES systems most closely mimic the natural photosynthesis you talked about, and that the solar fuels and artificial photosynthesis fields have been trying to emulate for some time now. And with them comes the possibility of us using direct sunlight and able to implement direct air capture of CO2 or CO2 fixation to create fuel, depending on the types of microbes and microorganisms we actually use. And these systems typically involve electroactive biocatalysts like acetogenic or methagenic cultures to make acetate and methane, respectively. And again, the choice of microorganisms is essential here in generating the yield, quality, and quantity of the products that we desire. So although plants and certain photosynthetic organisms can perform sunlight to fuels processes and CO2 fixation as they do in nature, these species have been found to actually be particularly hard to genetically engineer or tune to our interests. And so what people have done, for instance, in a study that was published last year, is they were able to successfully genetically engineer bacteria, specifically E. coli, to consume CO2 instead of their normal sugar or organic molecule diet. And with this ability to easily modify the genetic pool of the bacterium or microorganisms that are similar, and with their rapid growth rate, we can actually implement changes, we can see our ideas tested, and we can optimize on a much faster rate than we would with the other species. And we can essentially create effective and efficient biological factories. So this and other work in the BES, MES, and enzymatic fields is very promising, and it offers one of the many interesting routes to solar fuels actualization at a variety of scales and also across various applications.
Excellent, thank you, Oyen. So those are some complementary examples of how the field is evolving. As we were kind of talking about in the intro, I want to take a step back and think about kind of the arc of humanity's technology endeavors and ask, where does the solar fuel science currently lie? And what about the practice of solar fuels research do you think will evolve in the near future? And we'll turn to Jason for an initial answer on this question.
Thanks, John. I think it's important to recognize that we're currently at the beginning phases of being able to efficiently capture and utilize sunlight to drive chemical reactions. Over the course of human history, many large sections of time can be defined by the materials that humans use to create their societies. The stone, bronze, and iron ages come to mind. In each one of those ages, there's exemplary works of mastery of those materials. The pyramids and the samurai swords, or the megalithic architecture, I think are prime. I think that we're sort of at the outset of what will be known as the photon age. We're seeing evolving technologies, particularly in the fields of communication with fiber optics, lasers, with quantum information science, and I think also with solar fuels, where photons are going to become a more ubiquitous everyday component of our lives, apart from the standard illumination of our interior dwelling spaces. But with that requires a certain level of mastery in order to fully utilize the material. And so I think that it's important to recognize that we're just at the beginning of this and project into the future rather than 10 years, let's start thinking about 100 years ahead. We have a significant societal challenge to address global climate change and sea level rise. We have to get the carbon dioxide back out of the air. And stop utilizing fossil fuels to power our transportation and energy needs. So with that, I think that we should be thinking about how we want to grow and develop our society to be a clean energy society, one with closed energy cycles, and solar fuels is one aspect that's going to get us there. What's heartening, however, is that there are many different approaches for which I think we'll be able to touch on a little bit today. That give us a diverse approach so that we're not relying on one mechanism to get us there, one failure mechanism. I think people who trade stocks are know quite a bit about diversification of portfolios. And so I think that with that, we've got a lot of compelling options for the future.
Excellent, thanks, Jason. I guess to continue answering the same question, we'll turn to Shane.
Yeah, thanks, John. And Jason, that was a great lead into what I want to talk about now. To kind of wrap back into what John started the webinar on, he was asking us to think about system science. What are the system requirements and systems design of the overall device? And from hearing Oyen and Jason, your remarks, the systems sound very different in the different ways that we put this technology together. But at the same time, we can ask even more, I think, than just the system. what would be the end use of an artificial photosynthetic device? And so at least, I think in the past 2 days and maybe more historically, we're thinking about fuel generation. Of course, if we want to do that, we want to have good electrocatalysts, right? And electrocatalysts, we can be inspired from nature. If we're driving this in a remote location on some remote island, for example, we might need to couple photons directly or nearby to driving this process. In the United States, right, however, we might be able to have a solar photovoltaic farm somewhere generating electricity, or even the grid being able to manage this. And so I think thinking of the use, the application, and the specific application and where it might be is of interest. And so in particular, I want to bring up one of my favorites in artificial photosynthesis, and is piecing out one component of what nature has evolved over hundreds of millions of years to do really effectively. And that's take CO2 out of the air. And Jason, you just remarked on this. I mean, that's the elephant in the room. That's the big problem we need to think about now. And green plants have an enzyme called carbonic anhydrase. And this carbonic anhydrase enzyme speeds up the CO2 capture rate, the intrinsic rate, by over 1 million. Right? And so plants have evolved effectively to take dilute CO2 sources and do things with them to make fuel for the plant. And so if we want to make fuel, that's fine. But I think maybe as importantly is thinking about just a way to take CO2 out of the air, and again, mimicking natural photosynthesis. Now, I do want to say one more thing here. I'm getting a little out of my league. Okay, I'm trained as like a physical chemist here, and I'm talking about biochemistry and other applications. So I have to be careful here, but this really underscores something, right? That we can have these diverse ideas that involve many different aspects of science and engineering. But we have to be careful, right? If we go too far out of our, for example, wheelhouse, maybe we're reinventing the wheel or doing something that's either already a solved problem, or we're going down a road that's not our expertise. And I think this really underscores something. I think in yesterday's webinars is really apparent when the panelists were discussing their backgrounds and how they came into this field. They came from very diverse backgrounds. And so I think that A, that's important that we have collaborations, we have ongoing discussions, but B, that we change kind of the education and training of scientists looking to be involved in artificial photosynthetic research. And I want to give one example to wrap up here. This is my favorite. Sorry, some of you online might have heard me say this before, but if you come up to someone, a scientist or an engineer, and you say, I've got a certain mass of something sitting right here, right? I want to know how that mass can change. It can grow, or it can kind of disappear. It can gain or lose some of it in this physical location. Typically, I think if you ask a chemist, if you ask me, what I would say is it would go through a reaction, right? It would bind some other molecule, it would change, or be formed through a chemical reaction. I'm pretty sure from speaking to mechanical engineers I know, if you ask them, how do you change this thing? I think they'd probably say most of the time that maybe it would move, right? We can gain some of it by transporting the species in or pulling it out. And the good part is that both of those answers are right, right? We can move the mass, or we can form or remove it through a chemical reaction. But inherently in those kind of siloed disciplines, you're not normally thought as much to focus on these other aspects. Now, in particular for solar fuel science, electrochemists in particular are trained to think about both of those things. And I'd say condensed matter physicists, semiconductor physicists are as well. But my last point here would be, even in those two fields who are trained to think about both of those things, the equations that describe those processes have different names. You talk to a semiconductor physicist, you talk about drift and diffusion, or typically, I would say if you talk to kind of an electrochemist or chemical engineer, you talk about what's called the Nernst-Planck equation, which is drift and diffusion. Okay, and so I really think we need to kind of come together to have a common language that's really rooted in fundamental physics and engineering and chemistry, so that we can all be on the same page. Excellent,
thank you. Yeah, so I like a broader theme there of kind of creativity through diversity. And indeed, I think that's something that's particularly excited about the solar fuel science field, really embracing that. So it also, from those two answers, sounds like, this field is poised to put a lot on its shoulders as far as, where we want the impact to be and what I want our end uses to be in the future. So maybe, looking at that aggressive vision, what about the recent history of the field, thinks gives us momentum and reason for optimism to move into those new areas? And for this, I think we'll start with Oyen for an answer.
Yeah, sure. So CO2 as we know it today actually was conceptualized or invented, so to speak, 60 to 70 years ago. And it was just 40 years ago that the first flagship tests using metals like copper and silver were performed to convert CO2 to fuels like methane and carbon monoxide. And that was demonstrating a first key step towards practicality and commercialization. Since then, a lot of planar or aqueous system studies and experimental studies and computational studies have done a lot of great work and been conducted for us to understand the design space of this field of CO2 reduction reaction mechanisms, material properties, and the limitations of different cell designs. And more recently, we're at a stage where many in the field have been pushing the envelope on attaining higher records of CO2 reduction figures of merit, like current densities, which is just a measure of the rate of kinetic activity in our system, and selectivities for the fuels of interest, like ethylene and ethanol, as was discussed at length in yesterday's CO2 reduction panel. In the near future, where I think we should evolve, and we're already on track to doing this, is focusing more on commercializable systems like membrane electrode assemblies, or MEAs, that have a much better chance of exceeding the 200 milliamp per cm squared current density minimum required for commercialization. And planar aqueous systems, we know, and we focused on this in the past, and many are still focusing on them today, but they have been proven to be limited in terms of their current densities on the order of around 10 milliamps per cm squared due to mass transport limitations. So since we're all trying to get solar fuels or artificial photosynthesis or CO2 reduction to an increased level of technological readiness, we should begin to explore and investigate the phenomenon limitations of systems that are more commercializable. There should also be increased interaction and collaboration, as Shane mentioned, with fields that already have done this, have wet their hands in this. And we have an older sister field called the fuel cell community, or the fuel cell field. And that's one field we can reach in, learn from. We can learn from their cell designs, their materials, their route to real world implementation, and their findings and investigations, particularly around water management and ohmic or contact resistances in EAM FCs, and that's in anion exchange membrane fuel cells, because they have a similar pH and ionic environment that we in our CO2 reduction systems. And in those systems, there's a key component called ionomers. Those are solid polymer electrolytes, and also what membranes are made out of. And they also act as binders. And those replace the aqueous electrolytes that are used in planar aqueous systems. And it's very important that we start to think and learn such a catalyst layer, those components of the catalyst layer. And we need to start performing large-scale intrinsic kinetic studies for catalyst ionomer based systems, because we know that that's going to get us on track to a commercializable setup. We should also be dealing more with more fundamental efficiency and utilization issues like CO2 conversion, consumption, and fractional conversion, basically. And we can do this by using something that's come up in recent years called bipolar membranes, which help to mitigate that CO2 pump or CO2 loss effect in these cells. And we can also look at more improved cell designs. And as Shane mentioned, we have all come from very different and diverse disciplines, backgrounds, and experiences. And because of that, we tend to have different technical lexicons, but we can use that multidisciplinary strength to our advantage. A number of reviews have already stressed this in the last 2 years, actually, but it's important that we start to standardize our figures of merit. So when we're talking about current density, we need to start thinking of intrinsic current density. Is it normalized versus geometric? Is it normalized versus our ECSA? We also need to think about, when we compare a catalyst to another catalyst, we shouldn't just be comparing their fractional Faraday coefficients, but their intrinsic partial current densities to see if one catalyst as opposed to another is actually leading to an intrinsic increase in catalytic activity. And we need to make sure we're all on the same page in making a concerted effort and progress towards these figures of merit. So standardizing, no matter what cell we're investigating, standardizing our results and our findings is important. And lastly, we should begin to seriously look at the system materials and cell dynamics and how they perform in real world conditions. So exploring robustness, exploring sensitivity analyses, exploring stability, because we know It's nice when you have a cell that can reach high current densities and Faraday efficiencies, but it needs to last for tens of thousands of hours at the minimum. So we really need to start thinking of end use applications. So we know direct air capture should be something we should be thinking about in the near future, almost immediately. So we should start varying the concentrations of our CO2 feeds from 100% down the way to atmospheric or 415 ppm. We should start looking at the purity of the water we use. We can vary that, use seawater, use produced water. We can start looking at impurities and defects in the membranes to see how well this system and its physics can perform, no matter how much we perturb the system. And this was explored at length on Wednesday's panel as well. So in summary, basic science is important. It's really been crucial in getting us to where we are today, but we now need to look towards commercialization and practicality. And we need to look at the end use for all of these things we're investigating.
Thanks, Oyen. And I appreciate the perspective that we have and will build upon the kind of shoulders of scientific advancements in a lot of different fields. I'll maybe turn to Shane to kind of continue answering the same question about taking those kind of advancements and looking at where the field is moving.
Thanks, John. Oh yeah, you couldn't have said it better. That was excellent. I completely agree. We need to take what we're doing well today, move forward, have demonstration systems, standardization across the board. But piggybacking on what John said about kind of standing on the shoulders of giants here, if we look back in the history of how this field had developed, right, it developed I think, in kind of three different aspects that started everywhere from over a century ago to half a century ago. Of course, this is rooted in kind of solid state physics and semiconductor physics, right? The development of light absorbers and efficient solar cells came out of the advent of the diode, which was researched heavily in Bell Labs about half a century ago. And the diode, of course, has led to microelectronics, our advancement of microelectronics and switches. It allows me to use my laptop today and my smartphone and such. So extremely important, and I would argue that's something that we'd use today, right? If we want a demonstration today, we stand on the shoulders of those giants. Moreover, right, electrocatalysis and electrochemistry related to fuel cells and batteries and electrolyzers has also developed in parallel over the years, and we have fairly robust solutions to that. But one thing that's not included in those two so much is the real motivation of all the aspects of what plants have evolved to do. Just be absolutely amazing powerhouses for taking light from dilute CO2 feedstocks and making products, chemical fuels or food for the plant. And I think that's kind of gotten lost a little bit in recent years, right? Because we have such efficient other ways of doing this. But I think we should really hang on to the amazing history in that field and continue to push it forward and think of, in particular, unique ways that you can use light to directly impart chemical reactions, and even think about in the plan, these reactions are highly compartmentalized, right? There's not a big slab of material absorbing 100% of the light above its band gap, for example, right? They're not absorbing a lot of light. They're running at so-called low current densities. And so the catalysts have different requirements, and there's a lot of interesting science and engineering available there. And so, in particular, what I think is kind of a comparative technology is called photocatalysis, right? The cartoon image you draw of this are semiconductor kind of nanoparticles with catalysts on them or that aren't, but that these particles are specifically suspended in big, large reactors, kind of like these bioreactors you spoke of before, Owen. And, you can put these in the middle of the desert. You can have them running autonomously. You have to think about but now you have to think about other systems level designs and concerns one might need there. And so I think there are a lot of opportunities spanning basic science really to applied engineering all the way up to systems design related to, in particular, photocatalysis that we shouldn't kind of forget about. One thing I do want to add right at the end, and you touched on this as well, is that when you have a design like that and you think of this big bag filled with water, you might ask, like, how am I getting the water into the desert? And that's a very viable question that I think remains unanswered. We should continue to think about that too.
Excellent. And Jason, do you have any optimism to drop on us about the future here?
Yeah, thanks, John. I would like to specifically address a particular point in that there's a common comparison of setting up photoelectrochemistry against the electrolysis of water and wanting to choose a winner. And I think that that's a pretty reflex action for, it's very instinctual. Resources are limited, and we tend to want to select what is the best. But I think that comparison is being made because they're both evolving hydrogen. And frankly, electrolysis of water is incredible. The current densities that you can push are magnificent in comparison to photoelectrochemistry. That electrolysis of water is going to have a very critical role in generating the necessary hydrogen for our society. However, what I don't think that photoelectrochemistry dies on the hydrogen evolution hill. We need to think about how photoelectrochemistry can be utilized in a way to specifically target reactions that are ideally suited for photocurrent densities that match the solar photon flux. This is not going to be, high volume chemicals, for instance, and it may not be in ultra pure water as we tend to utilize for most of our experimental sciences. Ultra pure water, of course, is necessary for high efficiency electrolysis, but it may not be necessary for photoelectrochemistry. Particularly speaking, as ocean sea level rise continues to become an issue and fresh, clean water more scarce, reactions on seawater directly could become additionally more valuable. There's other ways to try to match this photon flux with, say, using dirty sources of water, like groundwater, wastewater, or I think Shane has an idea about doing it directly on air. I think a lot of people are starting to look at reactions directly on air, and so right. I think there's going to always be a place for photoelectrochemistry and photo-driven processes, and we need to, as we mentioned already, find a way to learn from each other rather than pit these technologies against one another.
Thanks, Jason. And I'm going to bounce this back to you in a second. I wanted to, I guess, note something because related to what you just talked about is the concept of the level of integration of different functionalities that we want to achieve. And this has been brought about in a few different contexts in this webinar series. It made me think of, what is our kind of most integrated technology that we use right now? And it's arguably like the integrated circuit in computing. And it's like, yeah, well, of course you want it to be an integrated circuit. We've always known that, except if you go back to the middle of last century and you walk into an early computer room, it's a room full of a bunch of different devices with wires connecting them. And it is a network of functionalities, but not anywhere close to the level of integration that we've achieved. And so trying to envision what exactly the integration looks like decades down the line is maybe something we need to not able to do and really need to keep the open mind about the real scientific challenges and opportunities for building. So I guess in that light, I think continuing what you were saying, but maybe pivoting to our concept of diversifying the end use of solar fuel sciences and how that will specifically benefit our concept of solar fuels technology.
Yeah, so, particularly we could imagine, say, 5 different examples of how we could use light to drive or to harvest energy from light with photothermal catalysis, photoelectrochemistry, photovoltaics, so PV plus electrolyzers, for example, photochemistry, and we might think photobiology. Each one of these fields is extremely well established at this point. Some new territories might be in thinking about how to combine them in unique ways, maybe doing photoelectrochemistry and photothermal catalysis at the same time. There's many of our catalysts are tested under dark electrolysis conditions. But there might be a role to play that we don't fully understand yet, having light in the reaction environment that might steer product distributions with photochemistry. And so I think these things need to be explored a lot more. Light also near surfaces might change temperature gradients. You might be able to impart a lot of different functionality if you start thinking of, in creative ways how to use light in a way that isn't just, say, shining it directly on your cell, but thinking about how to design the system to fully capitalize on having light in that environment. And I think this is really how, we have to lean on multidisciplinary science to get there. A lot of sort of modern approach is to throw a bunch of people with different experience in the research labs together, engineers, chemists, physicists, computational scientists, get them communicating with the same language on a similar or the same sort of problem, and just let them work together, and incredible things will happen.
Excellent, thank you. All right, Oyen, I'll ask you to provide some thoughts about, kind of moving forward beyond our traditional concept of solar fuels technology.
Yeah, Jason aptly spoke about the integration question, especially regarding PV plus EC versus PEC, light versus dark, and how integrating is something that we should be very open-minded about. And there are other integration questions that we can explore, like EC plus thermal catalysis, right? So from recent reviews, we've seen, and we better know now, that doing CO2 reduction to fuels makes the most sense if we are making kind of basic building blocks. So C1 to C4 or C1 to C3 hydrocarbons and alcohols, not so much any higher order chemicals. It doesn't really scale in that respect. But we can couple such systems to thermal catalysis systems that would allow us to reach those higher order hydrocarbons, maybe eventually even gasoline, and achieve CO2 polymerization, since they have quite a lot of experience in doing this successfully and efficiently for decades. And another interesting take is the conversion of CO2 to modern materials, in combining CO2 capture and storage to make cement, for example, so that the full cycle chain of CCUS, or carbon capture, utilization, and storage, is actually at play in these systems, and they're actually more of a circular economy, fully integrated system. And as a broader picture, you can think of it like this, right? You can think of us using these kinds of integrated systems to make the carbon fibers, rubber, and plastics needed to make a car, or any other vehicle, or any other structure or modern day technology or tool or utility. And lastly, in these systems, solar fuels can be broadened to look at non-CO2 feed streams, like using nitrogen, which we know is in great abundance in our atmosphere, to make ammonia, which is a critically important chemical that is partly responsible for humanity's recent advancement in the last century. And there have been some very interesting proof of concepts done already, published recently, in fact, for this exact electrochemical process.
Excellent, thanks. And Shane, if you could provide your thoughts on the same topic.
Gladly, John, thank you. Yeah, I mean, I think we've talked a lot about, in the last two speakers, about the reduction side of the reaction, right? That we're reducing CO2 to make things, we're reducing nitrogen, we could be making hydrogen. And we've talked a little bit about, where you might get water, that's the reaction medium, for example, for photocatalysis types designs, you may need a lot of it. But one thing we should never forget is that to have kind of a clean, renewable net reaction and net reduction reaction, we need to couple that to an oxidation reaction, and that better not make CO2 or we're in trouble. And so, really piggybacking on day one's, webinar event, where there was a lot of focus on oxygen evolution catalysis, I think really thinking about that the electrons are coming from water to drive this reaction, we shouldn't forget that. And moreover, we shouldn't forget that if you write a chemical reaction for oxidation of water, there are protons that show up too. Okay, and so managing both of those is extremely important. But to come to this water point, our planet right now is in real dire need of clean water sources. We've brought this up. I think all the speakers have brought this up in one way or another. And with our growing population, we're going to not only need water, but we're going to need food. And so, Oyen, you hit the nail right on the head, right? I mean, we're going to need to make ammonia from nitrogen. And if we can do this remotely in remote locations with PEC, that's really important. At the same time, there's a lot of nitrogen in the atmosphere. There's not so much water. So where are we going to get this water from? And we've all spoken, or again, there's been some comments before about maybe not requiring such high purity water. And so, the possibility of having large barges of floating materials out in the ocean and using the ocean directly is a really interesting idea, in my opinion. If it turns out, though, that, I'll call even the ocean a dirty source, we need to, maybe have higher purity water, one could get creative in using some of the solar photons that aren't going to generate these energized electrons and holes to heat up the water and drive a kind of a distillation process to distill the water directly from the ocean. And that would even probably be transferable to taking dirty water sources on the land. If we can distill the water, we can get clean water. And Jason, you already threw this, the bone to me here. I love this. My dream is, what if there is no water? There is no, H2O around that we can see as a puddle. How could we make this work? Well, we're lucky in our field because the amount of water you need to feed into a photoelectrochemical device is actually not that much, right? It's a substrate and there's a lot of energy in those OH bonds. You don't need as much as though it was a solvent. And so seriously thinking about capturing water from the air, I think makes a lot of sense. And here's a fun fact, even in the driest deserts that are like 10% relative humidity, that works out, the math works out that there's 10 times as many water molecules as there are CO2 molecules. So if we can figure out how to capture CO2 from the air, I think we can figure out how to capture water. And I think we should really think about that seriously. Yep.
Excellent, thanks. So we've got about 4 minutes here in this phase of the webinar. And so I'll kind of ask for some maybe closing remarks from each of you and bounce it back to Shane first and maybe, touch upon areas of science, whether it's directly in solar fuels or in the related technologies that we talked about, that is you think is most exciting and where we'll see a lot of kind of immediate advancements in the near future. Go ahead, Shane.
Yeah. Immediate advancements is the key word here, John. I'm gonna hang on that word alone. I'm gonna come back to what I just said. Just gonna repeat it. We need to take in water and drive oxygen evolution, right? But that catalyst is not that efficient. And so, I really think we shouldn't forget about that. We need to find a very efficient and active catalyst for oxygen evolution from water, and moreover, a reversible efficient catalyst. So that not only can we oxidize water to generate oxygen and our electrons to do the reduction reactions, we can then use the fuel and an oxygen source in a fuel cell effectively to do the oxygen reduction reaction, right? And I think there's really a huge need for that, even though, this has been a challenge for a long time. I think we really shouldn't forget about that. And so if we had such a catalyst, not only would we have efficient photoelectrochemical solar fuels devices, we'd have more efficient electrolyzers and fuel cells and metal air batteries. There'd be a lot of really excellent uses for such a catalyst, in my opinion. Thanks, Jeff.
Excellent. And Jason, your thoughts?
Right. So my core research interests are really in developing, techniques for ultra-fast spectroscopy. And so that's, and developing new materials for these photoelectrochemical applications. A lot of the new materials that we're growing in the lab currently have recombination lifetimes on the order of picoseconds. And that is far too fast to make a significant use of absorbed photons that are occurring on the femtosecond timescale. And so, I think picoseconds, that's a trillionth of a second. It doesn't really mean much. If you spent $1 million a day, every day since year zero, you would not have spent $1 trillion. So we're talking about a trillionth of a second is $1 in a trillion. It's extremely fast. Chemistry is occurring more on the millisecond timescales. We've got to learn, I think, in the field of ultra-fast spectroscopy and time-resolved spectroscopy, how to develop techniques to take our kinetic measurements on this time scale and determine what's going to happen on the steady state scale. So taking time-resolved kinetics and modeling steady state phenomena. I think that's what needs to happen, at least in my particular area of interest.
Excellent. And Owen, your closing thoughts in our last minute here.
Oh, cool. So there's quite a lot to be excited about in this field. It's a complex and interesting problem, and it's a privilege to work with so many smart people on this big global problem. But personally, what I'm most excited about in this field is the marriage between CO2 management and technology. And that involves exploring the fields of CO2 conversion, capture and storage, or any ancillary field really, and accelerating innovation, discovery, data collection, insight generation in those fields using automation, robotics, machine learning, or deep learning. And so with this marriage of CO2 and tech, there comes a path where we can potentially quicken our technology deployment. And it can reduce experimental costs if we measure it in terms of hours and days or loss of material. And it gives us the ability to quickly test out our ideas, build on insights, learn from mistakes and failures rapidly, and reproduce past work without probably going into a lab physically. And researchers can spend more time engaged in deep thinking, intelligent and insightful data analysis, and subsequent decision making. And PIs like John here have been exploring this very interesting cross-section for some time now, and other research groups are starting to do the same. And that's quite interesting to me personally. And in the next 10, 20 years, just throwing out some quick blue sky, things that are ongoing and we can start thinking about in the field, in the future of this field is, thinking of the full life cycle analysis of these technologies. Let's see if their carbon footprint really is negative. And broader exploration of system design engineering and circular economy, combining recycle of our reactant and our waste streams, and actually capturing from the air and storage and all of that. Implementing these technologies in fringe fields. So for instance, looking at solar or CO2 fueling stations in machines, in robots, in data centers, in backup generators for nuclear plants or chemical plants, or even space exploration vehicles like rockets, or on a moon base, or eventually Mars. We can think really big here and it's fun and exciting. And eventually when it becomes viable, maybe quantum computing could help us make actual realistic models of the multi-physics that happen in this very large system. All the interplays, all the interplaying physics, 3D physics, time-dependent physics. That'll be really interesting to do when we have more powerful computers. And lastly, unconventional advanced manufacturing. So a number of people, JCAP alums even, have been looking into 3D printing very peculiar cell designs that will allow us to overcome some of the utilization problems we are facing currently. So we have a lot of room for improvement in this field. We have a lot of room for people from different walks of life to work in this field. And we have a lot of room for cool and fun science to be done. And as a collective, we are very poised to do that. And I'm looking forward to it.
All right, thank you so much. Xeni, I'll turn it back to you to transition us into the next phase here.
Great. Well, thank you so much. Thanks, guys. Just a kind reminder, we have about 30 minutes for a live Q&A. So guys, everybody who's attending, I encourage you to submit your questions into the Q&A section of Zoom. It's at the bottom of your screen. And we'll try to get to these most of these questions today. We also, after 10:15, we're going to go into the quiet Q&A, and our panelists will just answer your questions online. So thank you so much. And with that, I'll turn it back to John. Thank you.
Sure. So we got a question from William pretty early on related to a phrase we said, driving chemical reactions with photons. So I'll ask Jason to weigh in on this question. The specific one is, what reactions are relevant, interesting, promising, other than water splitting? And I think an association with that question is, the other uses, more generally, the other uses of light in this technology.
Yeah, thanks for the question. And so we've been spending a lot of time working with carbon dioxide. And a lot of those reactions, as I mentioned, are dark electrochemical reactions. We see, a significant evolution of ethylene, of ethanol, but there's other products that are made transiently, acetaldehyde, for example. I think that there are ways to design electrochemical cells in order to extract transient chemical species. And or to optimize for particular targets. And so I think one of the knobs that hasn't really been turned yet is how the interplay of light in the reaction environment can manipulate some of these chemistries. By creating photogenerated charge at semiconductor electrolyte interfaces, or direct photoexcitation of precursor molecules, might be able to populate either higher order molecular orbitals that could change reactivity and select for electron transport mechanisms to particular orbitals. and or provide local electric fields that might be selective for certain chemical reactions. And or surface potential gradients, you could imagine, are also an option under illumination conditions. I guess that's all I have to say about that.
Excellent, thank you. We'll move to a second question here from Suraj, and I'll ask Shane and then Oyen to weigh in about, we mentioned bipolar membranes, and the question is, how far have we reached in using bipolar membranes in an MEA?
Quite far. There have been very recent demonstrations coming out of Shannon Betcher's group at the University of Oregon just about a month ago in making and demonstrating an MEA-based electrolysis cell that operated so efficiently that you couldn't tell the bipolar membrane was there in terms of limiting the conduction of protons and hydroxides. That the catalysis was the only thing limiting that overall cell, or so it seemed from the data. And therefore, I think we have really good, we meaning at least in that demonstration, really efficient bipolar membranes, and even a demonstration system in an MEA design that suggests this is definitely not impossible. It's probably a really good idea. What I would like to add to that, though, in the electrolysis type cell, these bipolar membranes consist of a cation exchange material. So those of you that don't know, it's a cation exchange layer and an anion exchange layer, and they're typically catalysts in the middle. And that material will catalyze either water dissociation or water formation at its interface. In most of the demonstrations thus far, the two membranes had very extreme pH conditions, right? Highly acidic cathode and a highly alkaline anode. And then the catalysts were chosen appropriately. So HER is driven in acid, no ER is driven in base. If you now want to talk about using that same structure to drive CO2 reduction, there become additional challenges in that, you may not want to drive your cathode, for example, in highly acidic conditions, because now you don't want hydrogen to evolve, and it happens very efficiently under acidic conditions. So you'd want a less extreme pH gradient across the cell, and that is possible. But when you do that, then the bipolar membranes inherently would have to have a larger rate of driving water dissociation and formation, because the rate is inherently enhanced by the presence of local electric fields. And when you don't have a large pH gradient, you then necessarily wouldn't have large electric fields. So, I think there's still a lot of challenges. And then when you're making reduced CO2 products, you have all of the challenges that you have in ion exchange membrane chemistry and physics and engineering of ion crossover and product crossover and plasticization and other challenges. And hopefully I left you something to say, sorry.
No, you answered that perfectly. There's almost nothing to say. I'll just point the person to a study that was published last year in 2019. I think it came from the Petru and Schmidt groups on using exactly this, bipolar membranes in an MEA type system for CO2 reduction. And again, it was done so that we can fix the CO2 pump issue. So in an ADM system, we have ions, bicarbonate and carbonate ions that are shuttling from the cathode to the anode. And we found that because of the pH differences on those electrodes, our CO2 is basically pumped back out at the anode. And so to mitigate that, we put a bipolar membrane in between so that we don't have that crossover of CO2. And as Shane mentioned, we have come quite far in this. That was last year. We already have some studies that are coming out looking at the computational that are computational studies and also supporting experimental studies for this exact system. And I think one of the major challenges is finding a catalyst, because there are many commercial BPMs available and you can make one in-house. But the challenge, I believe, still remains the facilitating of that autolysis reaction. So the recombination and the splitting of water in that interface in the middle of the BPM. finding a catalyst that can do that really well is still something we're looking into. But in terms of system design, it's already proven to be a solution to our efficiency issues.
Excellent. Okay, I'm want to get to here our highest upvoted question so far, and as a reminder to the participants, if there's particular questions in the Q&A you would like to see answered live, go ahead and vote those up so they come to the height of our attention. I'm going to turn to Jason to answer this question from Jose that's related to the purity of CO2 for efficiency and selectivity for CO2 reduction, and notes that we discussed the need to trap CO2 from the atmosphere, but arguably the most common ways to obtain CO2 these days are from enzymatic reactions like beer production and other industrial reactions like cement production that can produce semi-pure CO2. Thus, are there any studies or thoughts on how the purity of CO2 can influence the efficiency for CO2 reduction, and what would be a realistic source of CO2 presently?
Yeah, thanks, Jose. I think you've got, you've identified a particular sector. I think there are a lot of industrial sectors, commercial sectors that are generating CO2 that we might be able to utilize for either carbon capture or direct conversion. And so CO2 reduction in particular is extremely sensitive to contaminations. Particularly, at the catalyst surface, if you have, other metals around, things can change significantly. So if you're doing reactions on copper and you have a little iron, a little nickel, germanium, everything changes. And so, a common waste product might be sulfur in some reaction streams. And so I don't think that there's, a good understanding currently of how different contaminants in input gas streams can influence these distributions, but it has to be known. We also tend toward, using 100% carbon dioxide from, 5/9s, say for instance, CO2 tanks. But what would be really exciting is to see what we can do directly on air. And so let's not also forget the field of carboxylation chemistry. If we're not able to do direct CO2 reduction, if our catalysts are too sensitive to have toward contaminated input streams, perhaps there's other opportunities with using CO2 to carboxylate products, organic molecules, upgrade them to higher value chemicals and so forth. And photocarboxylation has been demonstrated already. Right, so if one doesn't work, we'll find other uses for these waste streams.
Excellent, thanks. All right, we'll move on to a new question that I'll pose to Oyen about artificial photosynthesis devices. Will they always be limited to deployment in ambient conditions, and what kind of the associated CapEx and OpEx burdens would be for such conversion devices?
Mm-hmm. Yeah, that's a good question. I don't believe they'll just be limited to ambient conditions. Even in the case, even if we don't do EC plus thermal catalysis, because we know that in that case, downstream will have higher temperatures than ambient. Even within the EC system and cell itself, there have been studies that have operated above room temperature. Some are pushing as high as 60, and that depends on the stability of the membranes and ionomers used. And so it's really a materials limitation that would determine how much above ambient we can go. And we know that with increasing temperature, we can increase our kinetics, but we also have to be wary about maybe some selectivity issues, catalyst layers, and possibly, again, some degradation that would happen as a result of those increased temperatures. Because we know that Joule heating effects are probably going to be a problem as we increase the temperature. On the other end of the scale, below ambient, the only thing I can think of right now that would apply to is in cryogenics, and that's in the separation of any products we make. So one thing that hasn't really been explored is how are we going to piece apart the different products we're getting in our outlet streams. So it's great for us to think of and to optimize towards very high periodic efficiencies. But even if we get 90% of what we want, there's still 10% of something we don't want. So we do have to look into different technologies that will allow us to separate out those streams, hydrogen from CO, CO from ethanol, all those things. And cryogenics and possibly pressure swing absorption, temperature swing absorption, or any of the other gas separation or liquid gas separation technologies would involve possibly low temperature systems. But we do want to use not just the catalysts, but also pressure, or maybe pressure, but temperature. We can use that in our deployment strategies. And how that would affect the CapEx and OpEx, I believe it's going to be a stability question. So if we are operating at high temperatures continually, I would expect the degradation rate to be faster. And that means that our OpEx would probably be really high because we have to start replacing and doing maintenance. On the other hand, if we need to get a very super membrane or ionomer that can withstand this thing, that would lead to a higher CapEx. So there are going to be trade-offs with these things, but we want a system that can last long and can give us the efficiencies we need. And eventually, the price will come down eventually when we start, engineering and innovating in that sphere too.
Excellent. We have another question here from David about our thoughts on scaling and the industrial scale of the chemicals industry, let alone the fuels industry, is tremendous. So how do we go from the centimeter squared, I think the kind of scale that we've talked about, it has been demonstrated, to kilometers squared or perhaps even bigger? I guess, Jason, you're nodding, so I'll turn to you first for.
Well, that was a mistake. I don't know if I have a good answer for that. I'm siloed in my academic institution. I don't think about costs, and I use precious metals for. I'm not sure I have an answer to that. I think that what academia and multidisciplinary science, large scientific endeavors that are focused on fundamental work are capable of doing are really, and where we're at is a demonstration of capabilities. I think our biggest value add proposition is spending a ton of money to show something is possible. And that last final phase of engineering the hell out of something, we don't have the person power and the dollars typically to carry something to a place that would be marketable. We've demonstrated that you can do direct synthesis gas production using CO2 input streams and water. We can tailor the CO and hydrogen composition to match whatever your industrial process needs to be. We've got materials that are stable. We've demonstrated, hundreds, thousands of hours of stability. Membranes are continually improving. And so at this point, I think that the next phase, we've got startup companies that are starting to take some of these technologies and figure out what sort of engineering challenges are required to overcome, these kind of inherent limitations that we can imagine. But in order to reach scales like you're talking about, gigatons of liquid or gigatons of gas and large volumes of liquid are almost unimaginable to me. And so, companies are going to play a critical role in carrying the technology to the next phase.
Yeah, great. Thank you. I guess I'll add some additional thoughts building on that. I think, from a lot of the scaling and chemicals handling point of view, like the incredible chemical engineering that's come from existing chemical and fuels industries can really be brought to bear on these new technologies. I think from the scientific point of view, and as Jason noted, we are not focused on scaling to kilometers squared. We're focused on the underlying science issues. But the question is, what science issues emerge as you start to do that scaling? And there's kind of reason to believe from modeling and figuring out how to dovetail with existing kind of scaling in industry, that the real challenges are to go from our millimeter squared to centimeter squared devices to like 1 meter squared. And once we get to 1 meter squared and solve the science challenges to get there, it probably is an engineering feat where we can build upon a lot of existing capabilities to go to kilometers squared and beyond. And I also want to note like another kind of way of thinking about that question of scaling. The one that might be even more difficult is the time scaling, right? So our fundamental science experiments last seconds to hours and maybe 100 hours. But as Oyen and I think others mentioned in our answers, we're looking for 10,000 hours beyond. And that's another scaling that time is also going to introduce new scientific challenges. And those are the kind of those initial scalings in both time and kind of centimeter squared to meter squared, I think, is where we'll see more concerted efforts in the science. And then, hopefully in a few years, we're more prepared to hand that off to industry with their kind of toolbox to scale further.
Can I add one more point, John? Sorry.
Please.
I'm just thinking there's going to be a significant opportunity space for someone who's knowledgeable to develop rapid stability testing protocols. I'm not sure what those look like. I think of these things operating in limited, temperature or flux regimes. And so how to do long-term stability testing in an accelerated way, there's definitely room there for someone to come in and say, this is exactly what you need to do in order to decide if your thing is going to live for 10,000 hours or 100,000 hours or 5 minutes, and do so in a way that's accessible to, graduate student and postdocs, a week sort of investigation.
Excellent.
John,
And Shane, I have a question for you, but do you have some remarks on this one before we move on?
could I say a quick thing?
Please.
Yeah, thank you. In particular for scaling, I think this is a great question, and it's great, as academics, I think about, centimeter squared to meter squared and say, and then we'll help it. Well, industry will help us move it from there. But I do think there's a real, so-called valley of death in taking even that size scale to get it to become a real device and commercialized. It's not going to be cost efficient to run that device compared to fossil-based sources, using fossil-based sources of fuel. It's just not going to be at that scale. And so I think we have to think critically about what other existing industries we can piggyback on that would find a lot of interest in having a meter, this meter squared type device that operates for a long time. And this also comes into the kind of social science of marketing and engineering products, right? I mean, I don't think, electric vehicles when they first came on the scene were, the least expensive, but people still bought them. Some people sometimes still bought them, right? And had pride in doing that. And I think that could also happen here. Just one quick example. I mean, I've thrown this around with some others at some point about, there's hydrogenation chemistry is needed for, some food manufacturing. And if we could use renewable hydrogen to hydrogenate something that goes into a food product, we have the right market to, I bet people would buy that product with a little, picture of the sun on it or something like that. And I think that's what has to happen. And that's what happens when technologies grow and then they get big enough and economies of scale, and then we're off to the races. So I think we can stand on the shoulders of the knowledge gained by the chemical industry. And I think our kind of dAdt partial derivative of the area with time will hopefully be steeper than theirs was because of that.
Excellent. And Shane, I'm going to bounce it back to you for a question from Bradley. For solar CO2 reduction, is using H2 as an electron donor a decent placeholder for H2O until water oxidation catalysts with the correct properties are worked out, or are they just too different for utilizing the same types of designs?
So using, I'm sure I got that right, using H2 as the electron and proton donor?
Right, which I think would be, maybe coupling CO2 reduction to H2 oxidation instead of to H2O oxidation.
Yeah, I think it's a great idea. I mean, I think having some sort of, we'll call it a cascade reaction to getting to your final product is a fantastic idea. I mean, I don't actually know what the chemical industry does in great detail, but I assume that this is something they do, right? You don't run a batch process. Again, I'm guessing here. Starting with some starting materials and end up with a 14 carbon chain unit product, right? You're going through different steps to get there. And so I think we can, follow that same type of path and be inspired from also the chemical industry and nature too. I mean, John, your first picture you showed of generating ATP and then ADPH and going in, and that goes in the Calvin cycle and adds a single CO2 to, a single molecule, and then that polymerizes, right? There are multiple different stages here. And so, yeah, if you can efficiently use hydrogen and use it as the electron and proton source to reduce CO2, I think it sounds great, but be careful. If we all are caring about the environment and global warming and CO2 levels, we have to ask where that hydrogen comes from. And, 9 out of 10 times, the hydrogen is not coming from a clean source. And, oftentimes from steam methane reforming, in which case it's giving off CO2. And now, now you have a closed cycle. If you're making a CO2 product, you can think about that. But just to be aware of that too. So maybe an idea would be to electrolyze water, to make the hydrogen and use the hydrogen downstream. But then we come back to the oxygen challenge. So I think I went around in a circle there, but hopefully I at least addressed a little bit that question. Good one.
Absolutely. I guess sticking with a hydrogen theme, I'll pose a question from Manuel to Oyen. What are the perspectives in hydrogen storage? It's a critical point in the development of hydrogen economy.
Yeah, like you said, Manuel, that's true. Hydrogen economy is going to be very important going forward, as well as the carbon dioxide economy, and they can very much feed each other. They don't have to be separate. As Shane mentioned, hydrogen is going to be coming out of a lot of our processes. So in a typical CO2 reduction cell, the whole challenge with Faraday efficiency is because hydrogen is so facile. Hydrogen evolution reaction is so facile that it's produced what hydrocarbons or alcohols we're producing. So even if, again, we are able to get up to 90% Faraday efficiency for our desired fuels and chemicals, hydrogen is going to find its way in there. And so instead of looking at it as a bane, we can start to think of integrating that into the hydrogen economy. So since we can either do electrolysis to get pure hydrogen, and we can use the hydrogen that's produced from our CO2 reduction reactions and channel that, separate that, purify that, and feed into the hydrogen economy, whether it's fuel cells or any other kinds of carbon neutral sort of technology. And what we have to bear in mind, though, is that even though it's going to come from a potentially carbon neutral or carbon negative source, the hydrogen still needs to be processed. So what happens, for instance, in my experiments, I end up getting wet outlet streams. I don't have dry hydrogen. I don't have dry carbon monoxide. So it's something that you can't directly use in some of your technologies. You have to dry it out. And so what is important in integrating this carbon dioxide economy into a hydrogen economy is how do we separate out that hydrogen? How do we dry it? How do we purify it? How do we compress it so that it's in a more useful form for that circular economy? So we shouldn't maybe look at it as oh, hydrogen, I'm getting hydrogen, it's a bad thing. We can use it somewhere, and people do need it.
Can I pick up a couple of points there, John, too? Sorry.
Sure.
In regards to hydrogen reactions with hydrogen and CO2, it comes to mind a thermal catalysis process in which there was a mixture of hydrogen and carbon monoxide, so synthesis gas under high temperature conditions, forming dimethyl ether, which could be a direct replacement for diesel fuel. How that works under photothermal process, has not been tested. And then, for hydrogen economy, I think transporting hydrogen is going to be an issue, right? I mean, you lose like 40% of your energy from hydrogen, just moving it around, liquefying it, driving it somewhere. And so these point of use generations are going to be necessary. So water electrolysis, for example, where say like a hydrogen powered, a long distance truck can come fuel, it seems like the necessary solution to that.
Excellent. So we got 1 to 2 minutes left here, so maybe we'll try to do a final question that I'll pose to Shane. And I think it's related to our discussion of the importance of capturing water. So the question is, why can't we directly incorporate existing atmospheric water generator technology into PEC devices to capture atmospheric humidity and produce water for water splitting and CO2 reduction?
Before Shane answers, this is a great question. I just wanted to ask, this is a great discussion going live, and I just want to ask you, John, and the panel, do you want to continue doing the live questions going forward, or you want to go into the quiet Q&A?
Well, I think we have more questions than we're going to be able to answer live. And I think if we divide and conquer with the original plan of typing for the rest of these questions, that'll be good. So we'll answer this last one live.
Okay, great. Thank you so much. So guys, after Shane is done, we're going to go into the quiet Q&A. Please stay tuned, continue to enter your questions. We will post them on our website together with the recordings. Thank you so much. Take care. Oops.
That's all right. I can speak over it.
Okay.
It's kind of
Yeah.
my lullaby.
So we're back to your last live question. Here you go.
Okay. Thank you. Integration of such a system with atmospheric water harvesting generation. I think it's a great idea. I think we should be thinking about that for sure. But I would also argue that atmospheric water generation devices are extremely inefficient in terms of the energy required to deliver a certain amount of water. I probably shouldn't do this rough back of the envelope calculation here. Maybe I won't, but I mean, at some point I was calculating that kind of the amount of energy, if you were to use solar to drive your photoelectrochemistry, if you wanted to also, supply the water you needed to drive photoelectrochemistry over, let's say, the course of a day, you would, on the order of need, to kind of double the size of your panels and your light absorbers, right? And so the AWG, and that could be off by a factor of 10 or something, but right, you need to use a considerable amount of energy to capture water, because what's happening is the water is going from a gas phase to a liquid phase. And in doing that, there's a huge amount of heat transfer, right? The latent heat of vaporization is being given off as heat. And if you don't do something about that, you're not going to be able to keep capturing water. In other words, you need to be cooling this actively. And so, I personally thought about the idea of, do we even need to go into the condensed phase? Can we keep it in the vapor phase and drive an MEA directly? I mean, I think there could be a lot of interesting ideas there, but that's not what atmospheric water harvesting generation devices do. And just my last point, and the reason they don't do that is because they want to generate water to be used for drinking and agriculture and, taking a shower and things like that. And in that use, water is the solvent. And water is the solvent. So you need a lot of it. For PEC and such, water is more of a reactant, right? Where we're breaking those OH bonds that have a lot of energy. So I know this calculation is right. I've done it before. If you had a PEC device and you wanted to run it an entire day, how much water would you need in terms of matching the area of the device, the solar absorber and the catalyst, with water kind of going right on top of it? For a whole day, you'd need 1 millimeter of water. 1 millimeter thick is all you need. So there are different challenges for taking water out of the air for PEC than for actually drinking and using it for agriculture. So I think there's a lot of room for very interesting innovation where we can not only couple light and reactions like photochemists do, but light reactions, water capture, CO2 capture, yada, 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 and really have them be synergistic.
Yeah, and Shane, I think there's new reports coming out with just taking CO2, bubbling it through water, and that's your input, and it works really well, and the stability may be better. You don't have to deal with all those pesky ions. So it works. It does work, and the efficiency is good.
Excellent. Yeah, and I think that topic is kind of a microcosm for a broader theme here that the number of different processes and fundamental phenomena that we need to bring together to realize different versions of artificial photosynthetic systems is quite broad. And it's not that each of them hasn't been demonstrated before, it's that they haven't been all tuned to work together in a holistic way. And so I think that's where the field is moving and where we have a lot of opportunity. In closing here, I want to thank the panelists for all your excellent contributions and the organizers, and thanks for the excellent questions that continued this conversation forward, and we look forward to continuing to do so with typing answers to the remainder of your questions. We'll try to get to all of them. And with that, we can close here, and we're ready for some nice music to motivate our typing of answers. Thank you.
Thanks, everyone.
Thank you.
Good. Thanks, everybody.